My name is Andrus, and we'll be talking about data frames in Java, two things that people don't know often that they actually can work together, and generally about data processing and data engineering. A few words about myself. I run this company called Object but I am a Java developer at heart. I started working with Java in like late 90s, and I do a lot of open source work. So these are my open source projects. Unfortunately, not enough time to like even introduce them normally, but one of them is DFlib, which we'll be talking about today. One thing I wanted to like bring your attention on this slide is the middle part. This is my kind of GitHub activity heat map, and normally for those familiar with GitHub, of course, normally it looks green. It doesn't look green here because it was actually generated by DFlib. So the beauty of data frames that you can actually you already have data for like nice visualizations, even though visualizations are kind of like external to data frames, and I'll show some of that in the presentation. So the main topic here, how do we process our data? And the answer to this depends on who you ask, really. If you go to like a data engineer, they know nothing about Java, but they probably work in like Python, very likely, maybe Scala. And they will mention data frames, they will mention Spark, they will mention a bunch of other things that normal Java developer usually doesn't touch. If you ask data analysts, the answer might be Excel, but we're talking about people who actually know programming and actually use programming for data. And in that case, the answer will be like, we use Jupyter notebooks and we program in Python, and again, we use data frames. And if you ask a Java programmer, the answer will be like, okay, so like, we're working from first principles. We're using like, lists, maps. Some people may not even understand the question because, like, of course, we work with data, we process data, and we don't need data frames. So we work with objects, right? And usually the result of that is that whenever there's a data project in the company, the management doesn't even come to us. They just go and hire Python developers. So if like there's a word pipeline somewhere, like in the conversation, it's usually like means it's not Java anymore. So the question is like, if we want to do data engineering, if we want to do data processing, what are our choices? Should we go learn Python, or like should we change something about our own ways? And the answer in this presentation is that yes, there are actually some pieces that are available, in other technologies that can be used in Java. They are available in Java. They're just not as widely known, and for no good reason, but they're there. So back to the basics. So to our objects and lists and maps. The natural way of modeling data in Java is to create objects. So if you have like a catalog of products, we actually want to treat every single product as its own thing. So we just create an object for a product, right? Here we have a little silly product with like name, color, and price, very few attributes, so each product is an object. If you have a lot of them, you put them in a list, you put them in a map, or whatever. So that's very, trivial, right? Very likely your product catalog is saved in some database, right? So, and databases, they don't have objects. So how do you like get them in Java? Again, everybody knows the answer. The answer is the ORM. One of the projects on the first slide was Apache Cayenne. That's an ORM also. So like I wrote an ORM, and I've been supporting it for more than 20 years. So I'm very familiar with this approach. And of course, it makes some assumptions. It makes that table is a Java class, and like a row in a table is an object, and each column in this row is an attribute, and like there are like relationships between them. But once you make those assumptions, you can write a framework that does this translation in both directions, and you don't need to think about a mismatch between like a relational model where people store data and your object model where people kind of process and display data. Unfortunately, it only works when the structure is fixed, right? When you know this mapping up front before you even started your application. You know that this table is this class, and this field is this column. It doesn't really work when you actually have the data transformation use cases. Data transformation means that we're not just changing the data, we're changing the schema, we're changing the the representation of the data. Like here I have, again, a very simple example. Like we're trying to create some analytical report of how many products in our catalog we have for each color. Like, so we start with products, and then we're doing some stream, blah, 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 collect, group by, and we end up with a map. So the interesting part is not the transformation itself, but the fact that, we started with objects and we ended up with some numbers put in the map. So different structure. So ORM is not going to help us here. And this is what all those other people who are writing data pipelines, doing data engineering, this is what they are doing. So they're doing this kind of like report generation, data transformation, and ETL, and so on. In Java, so Java almost kind of like gets in the way of doing this data transformation. I think this may be the reason why people decided, like the authors of Spark or the authors of like all the other tools and everything, they decided that we're not going to do it in Java, we're going to do it in Python or something, because first of all, like strong typing, so essentially like it kind of gets in the way of like representing all this like intermediate states. When your transformation, you just join two tables together, and the result you get just a few columns out of that result. And how do you represent all this like intermediate states? Like you do write an object for each join or something, and then like for each time you redefine some columns, or do put them in a map, and usually you'd put them in a map and you end up with this like deeply nested structures. So this was actually taken from one of my prior projects where I was trying to do data transformation with just like regular streams. But of course, streams are also, there are some other limitations with like streams. There are no joins. Recently, they added gatherers, which is great, which is kind of a step in the right direction. But then you need to write all those gatherers, so use a third-party library. But actually, I like where this is going. So the whole point here is like, why don't we model data as data, right? Not data as objects, but data as data. I think this is kind of important. Or like, in DevOps terms, they like to talk, for instance, like about, some servers are pets and some servers are cattle, right? So you have like, if you have like one server, it's your pet, and you configure it manually and everything. If you have like 1,000 servers, it's cattle. You want to have like a template to configure them all at the same time. So this is kind of the same analogy here. So if your product is a pet, if you look at individual product, if you build a report of how products are selling and everything, so they become cattle. So essentially, we need to switch from a representation of like each individual object is a row of data to like we have an entire table of data, corresponding to a certain schema or whatever. And this is what data frames are. So data frame is a synonym for table. So there's both are used interchangeably. In some languages they're called tables, and some data frames. I like data frames because table is too generic, kind of. So can we have them in Java? Is there anything that prevents, like, just any properties of Java that prevent us from implementing a data frame? So I tried to answer this question when I started this project here. And the answer turned out to be, yeah, of course we can have data frames in Java. Of course, it doesn't have as expressiveness of, I don't know, like Kotlin, or where you can have like DSLs or anything, but we still can, and it works reasonably well. So this is the library that I'm going to show you in a second, dflib, which stands, of course, for data frame library, and it's very lightweight. Its core is dependency free. So it's just another data structure essentially in your application, because just like a list or whatever, and that data structure is data frame. So it's like everything just goes around data frame and a bunch of different operations. And we're going to show you some of those operations in a demo. But before we go there, let me introduce something like somewhat related but independent: Jupyter notebooks. So if you work with data, so Jupyter Notebook is just a computing environment essentially that you can where you can run like little pieces of code in any language really. In the context of data processing, I call it Excel for nerds because this is how you this is like a nice way of working with data visually and still write code instead of just formulas and cells. So Jupyter is the environment that everybody in like data science, AI, data engineering, they using it like daily for to create their algorithms, to create their transformations and so on. Traditionally, people in Java just in the Java world, they don't need it, they don't use it, they don't know about it, or they think that this is something that can only be used in Python. Well, we kind of tried to prove it wrong because like it is. I think this was a missing component why like Java wasn't popular in the data world. So we took Jupyter is the most popular notebook environment, and it's very extensible. And J doesn't stand for Java; it stands for like Julia, Python, R essentially. So Jupyter is like this acronym. But because it already supported 3 languages out of the box, they had some architecture to plug in more languages, and some folks, like, I don't know, 5-6 years ago, they wrote a nice Java kernel called iJava, and then they abandoned it, they stopped supporting it, and it just kind of was sitting there. So we took it, we rebranded it, and we started supporting it. So we fixed all the bugs, well, not all, but like many of the bugs that they had. And right now it's a kind of nice supported kernel for Jupyter that doesn't have to be used with DataFrames, it can be used for anything, but it allows you to run Java on Jupyter. And for those who still don't understand what the notebook is and why we need it, I will show it in a moment. But to run Java, you'll need this extension, essentially, when you install Jupyter. Okay, so the demo here, the DataFrame demo is going to be about ice hockey. I don't know like how many people know anything about ice hockey, but it's not a prerequisite here. Like I work with the National Hockey League in New York for many years, and like I worked with all these data sets there, so like this is kind of a familiar territory, and lots of the things that they were initially written with like streams and objects, and like now we are doing it with like data frames. The topic here is ETL. Like ETL stands for extract, transform, load. So that's a typical task of a data engineer. So you would take some data from somewhere. It's just a fancy way of saying just like, grab some external data that somebody gave me, process it and save it in my own database for whatever purposes, for later use. So here we're going to take like a list of a CSV with hockey games and their outcomes. So it was actually taken like sometime during the season that just ended. And then we try to generate team standings, so like team relative positions, like in the championship, after a certain number of games. Okay, so let me switch to Jupyter, and I don't know if you can see it, but like it's not. But the command is just single command Jupyter Lab. And it starts a server and it pops up the browser here. And I have a couple of notebooks there. So notebooks is just a file, it's a JSON file with this IPYNB extension, and the extension comes from the Python world. So the important thing is that it's actually using Java kernel, and each cell here in the Jupyter notebook, I can run Java code. So some cells are just markup or markdown in this case. So just presentation, so you can annotate your notebook. It's kind of nice. And other cells are, can you see it, by the way? Okay, let me. So other cells are Java code, even though in the Java code you can add this like little directives that are specific to Jupyter. The formal term for them is magics. So like, I don't know who came up with it, but like, yeah, it's magic. And the good thing here, like you don't need the POM file. To add dependencies, you can just declare the thing right there in the notebook. It's completely self-contained. And I'm adding this dflip Jupyter dependency, and we have like a thin layer of integration with Jupyter. It's not needed really. You can use like just regular dflip code, just makes things nicer. And through transitive dependencies, it brings everything else that you need from dflip. So essentially, it's just like the same thing as a POM, just added a dependency in the POM. So I executed by hitting Shift Enter. It executed this cell and created a new cell. I can write some more code. Okay, so I mentioned the CSV file. So let me show the CSV file. Okay, so don't look at the data itself, but like I'm just showing you that it's a regular CSV file with a bunch of games and like game IDs and dates and stuff like that. So we're gonna create a data frame out of it, and everything in my demo from now on will be a data frame pretty much. So we have, you see in Jupyter there's a bit of a, it's not like IntelliJ or anything like, but it still helps you to discover your APIs, methods, and everything. So this is some auto-suggest. There's probably some AI extensions, but like I need to still explore them. So load, and I specify the location of a file, and it's going to be games CSV. And I can execute it. And I was talking something about like visual data exploration and everything. So it's not very visual just yet. So it actually worked. So it loaded CSV. But to see what Jupyter does for each cell, it actually tries to render the value of the last statement in a cell. And assignment is assumed to be void, so essentially it doesn't render anything. So I need to add this variable like here, just like this, even without like a colon, semicolon. And you can see the result. So that's a visual part where you're going step by step, and each step you can actually see the result. So it's with data, it's much better than debugger. Of course, you can do like this also in the IDE, but here like you can do the representation, which is pretty and like readable. So that's our CSV. And you see it's very easy to create a data frame from a CSV because data frame is a table and CSV is a table. So essentially there's like no drama. I don't need to define a class for each row. So it's all a data frame. So the next data frame, I'm just gonna use var because they're all data frames. So when writing a transformation, usually the first step is kind of like data source, your data set analysis and just understanding like what we need, what we don't need. Maybe we can throw something out and just focus on the relevant parts. So this is what we're gonna do. So we're gonna, for standings calculation, we don't need like game ID, date, arena. We only need the teams, we need the scores, and we need the overtime flags. So the first three columns are actually useless for us, so let's get rid of them. For this, I define a column set, and I can define as explicit columns, or I can define the columns that I want to exclude. So let me do this scene, game ID. So columns except these, date, arena. And once I define a column set, I can just select this column set, and this gives me another data frame. So it's a narrower data frame here, and we can start focusing on our standings. And let me show you what we're trying to produce. So we want to save the standings in a database, in a relational database in Postgres, and just this simple table, right? So it has team, it has points that we don't have yet. It has goal differential, which is how many goals were scored by the team minus the goals were scored against them. How many games they played, and finally a rank. So rank essentially gives us, their position in the standings. So from this we want to produce this. One thing you may have noticed is that each game it has two teams, obviously, and standings just has one team. So we need to split this into like statistics for a single team, single game. And just to save some time, let me actually steal this code from something that I prepared in another notebook. I'll show you what I'm doing here. So like I'm creating two intermediate data frames here, and I'm defining their columns as just kind of like home away agnostic. It's just like for centering on a team, no matter whether it's a home game or not. And then for each column that I defined, like see here, like I defined some columns also, and then I did select. I didn't provide any transformation. So here I'm providing a transformation. So for each column, I'm providing an expression. And if you're wondering if what the thing is, and some people told me, is it JavaScript? It's not JavaScript. So it's a static method on the exp class, essentially. So, and I mentioned about like DFlib integrating with Jupyter. What it does is just drop some imports implicitly so that you can start working without thinking about imports and stuff, and including this static import. So this was for the away team. This was the same thing for the home team. And the last operation is kind of like a SQL union. In DFlib, we call it vconcat, vertical concatenation, because you can concatenate horizontally or vertically. So it's like a union, and now we have a narrow data set here with just statistics per team. Okay, so now I think we can start calculating some of the values that are in our target standings. So it's going to be var df4 to df3. We define a column. Let's start with like goal differential, because that's the easiest to get. Goal diff, and this will help us to calculate points later. So instead of select here, I'm gonna do merge, and what the merge operation does, it works the same as select. Okay, I still need to write something here. Instead of select, just whatever you define in the column set, it just uses those columns in the result. Merge, it calculates the columns, but then it puts them in the original data frame, maybe overriding some columns, adding some columns. So essentially, it just like allows you to focus on the transformation, and like everything else kind of comes automatically. So here we need to calculate the difference between score and opposing score. And here, so there's one trick here. First of all, this thing came from a CSV. So in CSV, everything is a string. Like we can do arithmetics with strings, so we need to do a conversion to integers, and we could have done it like, I don't know, kind of like Pandas does it automatically when you load a CSV. But we're trying to be performant. It's a production library, so like we're not doing transformations that nobody asks us to do. So by default, CSV comes as columns, as strings. So we need to do the transformation here when we start doing arithmetics. So I take a column score. Actually, let me type it. So there are like column is just like any column, but there are columns of a certain type. So I'm saying it's a string column, and we can do it. We can cast it to it as integer. So it will just do a transformation. And once we cast it as an integer, we have a bunch of like arithmetic operations there. And we do the same thing with the other column. And by the way, in the new version of, in the next milestone of DFlib 2.0, we're going to have like a little expression language. So here we're creating expressions using API, which is actually easier to write but harder to read because they're longer. So once the next milestone goes out, there will be two alternatives. You can just write a string expression. Okay, let me see. Okay, if all my parentheses are balanced. Okay, so now we have a new column in the was added to the data frame, and this is a demonstration of what I mentioned before, where in Java we need to like define like a new Java class if you want to have like an extra property, right? Or we need to put it in a map, and then like things become murky there. So here you can add, remove columns. You can do whatever you want with the columns, and you don't need to define any new structures. It's all a table, just a table with different columns. One other transformation I wanted to do here is I want to transform over time, and I think so. Here I need to explain how points are calculated in hockey, or at least in North American NHL hockey. So for each game, a team can get either 2 points or 1 point or 0 points. So 3 outcomes. If they win, they get 2 points. If they lose, it depends on how they lost. So if they lost in regulation, in like the first 3 periods of the game, in like normal time, they get 0 points because they just lost and that's it. But if there is a tie at the end, like if it's like the score is still like 0-0, like at the end of 3 periods, or 1-1, then there are no ties. So essentially, somebody needs to win the game. So essentially, what happens? They keep playing. They play like another period, or like however many, depending on whether it's playoffs or regular season. So they play like an overtime period, and if somebody scores, they won. They get 2 points. The losing team gets 1 point. If by the end of overtime they're still tied, nobody scored, they want to save time. It's not like American baseball or whatever, like where they just keep playing. So they actually instead of overtime they go to this period called shootout, which is just like one-on-one penalties. And this is a very quick way to determine a winner. But the outcome is the same. So essentially, the winner gets 2 points, and the losing team gets 1 point because they persevere, for a longer time, so they get awarded 1 point. And so, like here, in this column, we're seeing like overtime and shootouts. So we're seeing like all these outcomes. From the point calculation perspective, we only need like true false, overtime, not overtime. So let us simplify this column a little bit, and just convert it from multiple strings to Boolean, to a single Boolean, or to true or false. Oh. Okay, so we don't have like a ready transformation, so we can just put a custom lambda. So we just map it to a Boolean value, and we just want to say that S is not blank. So if it's blank, then it's not overtime. And by the way, those like empty cells are not nulls; they're blank. So it's we didn't configure the CSV loader to do this conversion for us, so it's blank strings. And if there's something overtime or shootout, then this was overtime. Okay, execute this, and you see the overtime column got merged, so the old one got removed, and like the new generated column with trues and false, it got put in place. Again, you can do it with tables. It's not easy to do it with objects. You can do it with maps, of course. Okay, so we are ready to calculate points, I think. So with points, we're gonna add another column. Oh, and by the way, like, have you noticed how I executed the previous cell once, and then I thought about something. Oh, I need to add something else, and I went back there, I edited it, I re-executed again. I didn't need to start from the beginning. I didn't need to restart the notebook. So that's this is where it's very very different from our like normal workflow where whenever we change something in a Java application we need to restart it and start from the beginning. So here, and this is why like scientists and data scientists like it, because sometimes you load a data set that takes, I don't know, like 10 minutes to load, and or maybe longer, and you don't want, like, whenever a small change, you don't want to reload it again. So that's the beauty of Jupyter, but that's kind of like tangential to the DataFrame itself. Okay, so let's calculate another column. Okay, and this column is going to be, so we have another expression called if expression. So like if so we're going to determine the winner from goal differential. So if the goal differential is positive, then this was a winner. If it's negative, it's a loser. So there are no ties, so there's not going to be a zero, because even in shootout, they give you like this like fake goal, essentially. So we say goal differential greater than or equals then 0. So and if that's the case, then the next expression is executed. If not, like the third expression is executed. So the next expression is going to be 2 points. I need to wrap the number. Oops! I need to wrap the number in this val expression. It just generates like a column with the same value. And if it's not true, if it's a loss, we need to like fish for this overtime point. So then we do another expression. And it's already a Boolean, so it's much shorter. And now we do val, if it's overtime, val 1. Okay, need to balance parentheses. Okay, so now we have points, and they kind of make sense. So, like, oh, wait a minute, doesn't. All right, so here we go. So this is why visual kind of development rules. So now we have all the statistics per game. So we have 1,780 rows right now. We need to get it down to like however many teams there are. There are 32 teams in the NHL right now, so we need to aggregate it. How are we doing aggregation in databases and SQL? We're using group by, right? So in data frames, like there's lots of analogies with SQL really. So we also do in group by. So there's a method called group. And we're going to group by team. And everything else is the same. So it's kind of like we applied expressions to calculate the columns of the same size. In aggregation, we also apply expressions, but instead of just producing like a column of the same size, it produces a single value for a column. So you give it a column and it produces one value. And because we are within a group by, there are going to be multiple groups, so there are going to be multiple values, but fewer than the original. So let's define the result columns. We want team. So we already get into to this data structure. So we want team, we want points, we want goal div. There's more stuff, but okay, let's do it incrementally. And here, instead of merge, we're doing aggregate. So, but it works the same way, just that expressions are going to be used in this aggregation context. So for the teams, there's nothing to aggregate. We just say team. For the points, we do int points sum, and the same thing for goal differential. So it's very simple. Again, like if you work with SQL, you should recognize all this, not the syntax, but the kind of the idea. Okay, now we have a small data frame with already like season statistics that gives us kind of the idea where the teams are against each other. Let's also add this games played column. Games played, and there's no column to calculate it from. There's just a function called count, expression called count. So we have games played. All right. Rank, and so the final kind of final step is to calculate the rank. So how are they ranked against each other? And for this, let's first sort it. Again, same as SQL. So you can do group by, but you can also do sort on columns. And sorting is also done with expressions. And the first thing we're going to sort on is points. And we're going to sort descending. So essentially, the more points you have, the higher up you are. So you see here, so it's already sorted, but sometimes you see there are like 3 teams here. They have the same amount of points. So we need to keep sorting. So we need to decide who is better there. So like we keep sorting by another column. So the next differentiator is games played, but the direction is different. So the direction is ascending. Because the fewer games you play, more points per game you have. So essentially, we consider you better. So we resolved some of that, but there are still 2 teams that have the same. Oops, no, these 2 teams, they have the same games played and the same points, and this is where goal differential is used. That's the last criteria. Sorry, let me just copy it over. And it's also descending. Okay, so this is our standings, and we are ready to add the rank column just in case somebody in the database just insert them in a different order or whatever. So we don't want to rely on the order. So we're going to insert a rank column, and I'm going to merge. This is a very simple expression, a raw number. So once everything is sorted, the rank is raw number. So this is our standing. So we were doing ETL, right? Extract, transform, load. This is extract was the first line here. So this was extract. Everything else was transform, transform, transform. So this is what dflib is for. It's for data transformation. And finally, we need to load it. We need to save it in the database. And we started with CSV. We'll save it in the database. Doesn't matter. Data frames they're not connected to any data source. It's just data structure in memory. You can read it from one place, store it in another place. So it's very good for moving data even without transformation. Let me actually to connect to a database. I actually need a little connector object, just to save some time. So connector itself is not interesting, but it allows us, it opens the whole database world to us, so we can store and read data from there. connector. So we're going to pick something called table saver, and the table name is standings. Again, the difference with ORM is that we're defining what table it goes to right here, so we don't need to pre-map it somehow. So it means that if you have lots of data, you can like save it to different tables and like create your own kind of approach to where the data goes, all in the code, and then you just save it. So there's like really very little like ceremony. So something is off. Okay, games played. Okay, the column names, they actually have to be aligned with the table column names, but renaming columns in DataFrame is very easy. So this is like aligning the schema can usually be like the last step. And okay, games played. Okay, I don't need to rerun the connector. Okay, here we go. So we generated all the SQL needed, again, because there's a table in the database and there is a data frame that is a table. So you just very easy to generate SQL. So I didn't need to write an ORM to create like this connector for the database. So this is kind of ready to ship. You can just like take all the statements, put it in your Java application, and just put it in a cron somewhere or whatever scheduling approach you're using. I don't know. The only trick here is that we need to make it a little more robust, because if I go here and I re-execute it again, it's going to insert another 32 rows, which is not what we want in a job that runs periodically. So we would like to be able to merge the data somehow. And I know many people, they are not, they don't bother to actually do merging. They just like delete data from the table and reinsert again. And then, somebody is receiving like, 10 million events, whoever is listening to the database changes. So here we can actually do something smarter. We can do a merge by like certain set of columns. So here we can just merge by team. So if I re-execute it, so it just like it's smart enough. It just tells you like no updates, not everything is unchanged. And so what it does, it does a select, it generates a select automatically behind the scenes, and it gets another data frame and takes two data frames and does kind of a delta on them, diff, and based on the diff, it can generate like inserts, updates, deletes, or nothing in this case. Okay, so this kind of concludes the ETL. So we finished ETL. We stored our data. This data can be displayed on the NHL.com website. I wanted to show you something else that is kind of not ETL related, but is still kind of cool and data frame related. And this is charts that I mentioned in the beginning. I don't know, how many of you have like ever in your life, in your professional career, done charts in Java? Okay, here we go. Oh, quite a few. Nice. What library?
Bird.
Okay. Okay. All right. So I like go in like further out there when when people were still doing like Java applets and stuff. So yeah, there were some commercial like charting packages, and they were fairly good, but since then, of course, all the visualization, it moved to to other technologies, to JavaScript in particular. So all the cool stuff, all the visualization stuff happens in JavaScript. So we were like, okay, so we implemented a data frame, like they have them in Python, they didn't have them in Java, but we're not going to implement our own charting package from scratch. This is just too much. So we took one nice JavaScript charting library called Apache eCharts, and we created a Java DSL for it that will generate these charts. It will spit out JavaScript essentially. And since we are in a browser here, this JavaScript can be displayed. Because it's an eCharts integration, it starts with eCharts factory, static factory method, and we can create a chart. And what can we map in our data set? We can probably do like points by team. So we define x-axis as team. So it's because data is already prepared, so the chart itself is kind of easy. Then for y-axis, we can add multiple series. So I'm going to define series and define like what type of series there is. And this is where all the types that we support currently, each chart supports more, and we keep adding them. So like this heat map, remember I showed in the beginning is a kind of like a fake GitHub activity. So that's this heat map calendar type of chart. But here, we're just going to do a bar chart and bar chart of points. Okay, and we're ready to plot. So here we go. So like it's really like this little one-liner because the data is already there. So and eCharts does all the nice stuff, and like our goal here is to glue the two together, and like it's very easy. So of course, if you want to change fonts or anything, like it's a little more involved, but still, like by default you get this, and you can already like watch for trends and stuff. Let's also maybe map goal differential. We're probably going to see something similar because the teams are ranked. But you see, it's like, let me actually change it to line. You see, it's non-linear, so essentially it's like, it tells us something, maybe tells hockey analysts something, and we can actually combine the two. Okay. So we can get this for nothing, really. All right, so back to the slides. Okay. So yeah, we learned, we had like a little preview of DataFrame API. What I didn't show in the demo, and like I'm sure it's in the back of someone's mind, is like, does it support joins? Yes, it supports joins, so you can join two data frames coming from different sources. For instance, like one from CSV, another from database. You can still join them. It does support window functions. Yes, it does support window functions. So you, like for instance, ranking, I think we could have calculated without sorting, just doing it within a window function. Okay, so it's this API that kind of like, functionality-wise, it's somewhat equivalent to SQL, but you have it in Java and you can do it step by step. Now let's take a look at some other aspects of it. So performance, and I know performance, like all benchmarks are very easy to fake because you can always like pick, where you use the strongest, and this is what I did here. And so essentially, like performance, again, it warrants like its own presentation. It's a very long topic, but like I just want to show you one number. So like we have like 2 million integers, and 2 million is not significant. It's just like a lot of integers, ints, primitive ints. And we store them like on the right hand side, we store them in a data frame as like 2 columns, and like on the left hand side, we store them as properties of an object, as essentially fields in a Java class, and that is itself stored in a list. So the difference looks like this. So this is the difference for a single int. So essentially, it's how many bytes it takes to store an int. And it looks very dramatic. And like I said, I'm picking my own benchmark, so I made it dramatic. But it still demonstrates something about sort of like treating data as data versus like modeling data as objects. And if I don't know, you know what for means like in a data frame column. So for, it's like a size of int in the Java specification. So whatever scaffolding around it, the data frame provides. When a data frame is big enough, it's like insignificant essentially. So and if you model it as a list of objects, yeah, you pay for all this memory. Of course, like I said, if you start looking at strings, things become more murky. Of course, with numbers, it's like more dramatic because strings themselves are objects. Okay, so since like I know people who are coming from like data engineering background and everything, so they understand what data frames are for, and but people who are not and who are still like who are on the Java side and didn't leave us and didn't go into Python yet. So I think this may be helpful. So essentially, just ideas of like why is this useful for me, and to me, it's like, first of all, you can start doing data exploration. So something that's like, kind of like no commitment. You just got a data set and you're trying to understand what's in the data set. So kind of like you would load it in Excel and just try to like look at it and like understand what's in it. But if there are like millions of rows, you can't load it in Excel. This is where Jupyter is helpful, even though it's not needed for dflib as such. And the example of that is the second bullet point, ad hoc log analysis. So this is something that I'm using a lot myself. So like, for instance, NHL, in addition to all this like data projects, they have like regular web services that are serving the same stand-ins to the website or to the mobile app. And they generate a lot of logs because, of course, there are millions of people coming there every day, millions of hockey fans. And when things go wrong, I just get a chunk of logs from the log collection system, drop them in Jupyter, and with the help of dflib, I can just focus on first of all, I can filter the request end and like some request statistics, and just maybe chart where the slowest requests were, and maybe narrow down on that part and start digging into like other logs, like other like SQL queries slow or whatever. So I can do all this like ad hoc playing with data, with pretty big chunks of data. So like right now, I mean, this has 48 gigs of RAM, but you can get 128 or whatever. So like you can store a lot of logs in memory. So anything that's already tabular, either on the input side or on the output side, it's very easy to represent as a data frame. No drama. You just like you load it or you store it, table to table. So in memory table versus like on disk table. We've already seen we saw the ETL examples. My last point here. I think that's a good one, because when you do an ETL, you really don't care about objects at all, because like ETL is just to prepare data for somebody else, and all your intermediate states of objects, they have no representations, they have no business kind of, I don't know, name, or like you can't explain like what a join is to to somebody who asked for this data or something, like what this join represents like in the midst of your transformation. Or like, remember in the demo we were like dropping columns and adding columns. Like each one of those representations, they don't have a name, really. It's just the table. So I think this kind of like makes a Java developer, just turns them into a real data engineer. So whenever people start talking about pipelines, what's inside the pipelines is DataFrame code. So a few conclusions. Like, we still have a few minutes here. So we are. So DataFrame is a Swiss Army knife of data processing. So lots of operations already available out of the box. Kind of parity with SQL and more. Well, I mean standard SQL, because right now people are doing all the crazy things with SQL too. So like, it's no special infrastructure required for those people for those who are used to like Spark. Spark is great. Just like together with Pandas, it inspires lots of things that we are doing. But Spark, you need to write applications in a certain way, package them in a certain way, and deploy them to the cluster, and pay Amazon for all this cluster. And of course, it allows you to handle much bigger volumes of data. They don't have to fit into a single computer's memory, but there are trade-offs. It is very similar to SQL, but it's composable, so you can like debug every step. Like, try doing this with like a SQL database. It's not a replacement for anything, but it has a very specific niche essentially. And like, once you understand this niche, you start seeing it in your work, and it's just a tool that helps you to solve certain type of problems that are everywhere, and that we just kind of ignore it like most of the time. And finally, notebooks and charts, don't overlook them. They are not required for any of this, but it's just like another tool in your toolkit that help you to do things that otherwise people are not used to doing in Java. Like, this is why I asked about charts. So okay, I'm actually interested that people still doing some charting in Java. That's great. All right, so thanks for coming here. Yeah, I'd be happy to answer any questions. Questions? Yeah, here we go. This microphone here.
Okay. I was wondering whether you could build something like DuckDB on top of dflib in Java.
Theoretically, you can, but I think the harder parts there is going to be like essentially working with persistent state and stuff like that. So where you need to like partition your data somehow or load them. But yes, the answer is pretty much yes.
And maybe another question. but I think you partially answered it already. But is it possible with DFlip to load a big data set partially into memory on demand? Like if I don't only need a certain data range, so to speak, and I don't want to feed in the terabytes in memory or something like that.
So it depends on the connector. So for each connector, we are trying to create these optimizations to make it possible. Like, I don't know, if it's a Parquet file, like we want to load certain columns, like, yes, you can. Like with CSV, it's harder, but you still can. Like you still load everything, but it's going to be just a stream in memory. It's not going to be converted to objects. So the answer is yes, but sort of your abilities depend on the data source.
Maybe another question. How do you handle conversion error? So your dataset contains no mistakes, but you know data quality is a real issue. So, and we see that you did map a castable and so on. So, but in case in the columns the type does not match what you did, how do we handle error? Do we have any strategies to handle that?
So yeah, I mean, there's no magic, of course. You need to sort of understand your data set, and like, you know, this DFlip will help you. Like, you know, you can inquire the type of a column and you know, just check what it is and what conversion needs to happen. Currently, there are no like automatic conversions because like we sort of again, we never prioritize it. We can probably make it a flag and like an optional scene or just like detect types. And we can do that. Like there's no API, but like if somebody asks for it, we will add it. So it's like all the groundwork is done. So yeah, it's just a question of priorities and it's like what the user is asking for. But as far as like cleaning data sets, like yeah, there are some data sets where like, you know, there are like, I don't know, false is represented by you know, a dash or something. You'll have to write those transformations just like I showed in the demo. So, but you need to understand them. So first you see it. Then you can do like some analysis. Like for instance, you can do like some analysis of like what is the cardinality of this column and like what values are contained there. And then it's like, oh, there are like dashes and empty strings. So this is the two choices I'm working with, and then you write a transformation to like convert them to something meaningful.
Okay, thanks. I was thinking of something like skip bad row or something like that.
Well, I mean, you can. So in addition to like, I didn't have time to show everything, so I showed like column sets, but there are also row sets, and you can say that okay, so rows that you know, match or don't match a certain condition, you know, just throw them away. So you can actually, yeah. So with row column set, I kind of like the API. Like we added it like late last year, and like previously we were trying to just like add single column. Like it wasn't scalable enough. So right now we can define this like column set and a row set, and then you can either replace the values there, like recalculate the values, like add something there, or just get rid of it. Just like wipe it out of the table. So yeah. Oh, this is not good.
One last question. I played with DFlip in the past with version 1 dot something.
Okay.
And today I learned that there will be a version 2.
Yes,
what are your plans for version 2?
Okay, yeah, so version 2, we want, first of all, like, we did some benchmarks like against others. I know it's kind of silly, but like we want like to have the best performance, right? And like aggregation, for instance, everything like we were like great. So like we were faster than like most of the things that I tried. But like there was like a very slow thing that is involved like one BRC like tasks where you need to read a CSV, right? And reading a CSV, we were using like a stock library, Apache Commons CSV. And this was a bottleneck everywhere. So if I remove the CSV step, like we're the best. And if I keep the CSV step, then it depends on how big the CSV is. So essentially, like we are like totally like we're implementing our own CSV loader right now. And I had a call this morning with my colleague, and like we already like, you know, have a prototype of that. We are adding this expression language essentially, and expression language is already there. So like I was like thinking to myself, like I was almost ready to release it before the conference, but then decided against it because I didn't want the demo to go down. So there's going to be that, and we started to think about some streaming approaches essentially, and like it's still kind of like vague, but yeah, we want this like micro batching, like in one machine essentially, not in a cluster, but like in one JVM. Yeah, so that's the direction. Right.
Thank you for your presentation. And I asked for the implementation question. Do you hold everything in heap memory, or have you facilities for using off-heap memory?
It's so by default it's all in the main memory. And we are thinking where off-heap would actually make sense, because like we thought it would make sense for CSVs, but like then so essentially for a specific storage format. But then it didn't, at least not at this stage. But so we are thinking in this direction, but right now it's all in the main memory. So because like when you go off heap, you already need to like sort of like figure out like the serialization and stuff. So maybe like Arrow, some Apache Arrow, maybe something like that. So we are looking in that direction, but probably not in 2.0. It's probably going to be like 3.0 or something. Yep. More questions? All right, thank you very much.